Alright, logarithmic functions. Sounds really intimidating because you never heard it before, but they're actually not that bad. It's probably, out of all the things that we do in this class, people probably do the best on logs, or, not the best, but it's up there. So don't get intimidated by the name. Let's just jump into it and do it. Alright, so logs are just the inverses of exponential functions. So just like if you took f of x equals x plus 2 and switched x and y and solve for y, you would get f of x equals x minus 2. If you look at the bottom, b of x equals 10 to the x power. If you switch b of x and you solved for b of x, you solve for y, you would get the log of x base 10. It is just the inverse of an exponential. It helps you figure out, if you wanted to know, what power do you raise 2 to get 7? Well, 2 to the second is 4, 2 to the third is 8. It's got to be somewhere in between 2 and 3, the power you raise 2 to get 7. How would you figure it out exactly? You would use logs. It's a way to solve for the value of an exponent, to get a variable out of an exponent. So one reason why I love logs is because I love breakfast. Bacon and eggs. Great way to start every day. If you look at the log on the left, on the top left, log BAE. Alright, so that's the form. That's called logarithmic form. The little b represents the base of the log. Every log has a base. And then the a represents what you're taking the log of. A lot of times you'll see parentheses there, but the b will still be there too. That's a. Equals e. What do those letters mean? If you were to put it in exponential form, the base of the log is the same as the base of the exponent. And the answers, when you do the log of a base b equals e, e is the exponent. And what the exponential function equals, the answer, is what you take the log of. So when you go from log form to exponential form, think bacon and eggs. If it's written in this form, equals e, log of a base b equals e, you're going to look at the first number as b for bacon, and that's the base of your exponent. The second number you see, a for and, is the answer when you raise b to the e power, e eggs. So this is only true when x is greater than 0. When x and a are greater than 0 and a doesn't equal 1, y equals the log of x base a. So that's how it's read. You say the big number first and then the base second is equal to y equals a to the x power. So that's just going from here to here is using bacon and eggs, base answer exponent, way of converting log functions to exponential functions. So let's do it with actual numbers now. So if I said convert the log of 49 base 7 to exponential form, well, your base is 7, your answer is 49, and your exponent is 2. So in exponential form, 7 to the second power is 49, right? And you do it for your bae, because she would want you to learn about logs. Here, we have a base of, so now it's an exponential form. So 13 is your base, 2 is your exponent, and 169 is your answer. So in log form, it's going to be base answer equals exponent. Alright, now what is going to happen is you're not going to know all the numbers, you probably won't know one of them, so converting from log to exponential form or exponential log form will help you solve for one of the variables. So let's do that. So evaluate the log of 81 base 9 without a calculator. So you'll be able to do these in your head, but at first, write them out. So that's your base, 81 is your answer, x is your exponent. So 9 to the what power is 81. That's what the log of 81 base 9 is. It's what power do you raise 9 to get 81. So the answer is 2. Here, in exponential form, it'd be 27 to the x power equals 3. So the cube root of 27 is 3. So x is going to be 1/3. Alright, number 4. 4 to the what power is 32. So base, answer, exponent. So base is 4, answer is 32, exponent's x. So first we have to take the square root of 4, and you get 2, and raise that to the 5th power, and you get 5/2. Right? If you squared 4, you get 16. If you cubed 4, you get 64. So you know it's got to be between 2 and 3. So when that happens, you take the root of the number first. So square root makes it a 2. and then raise that to a power to get it to whatever number you want it to. Alright, whenever you take the log of 1, it's always going to be 0, because anything to the 0 power is 1. Anytime the base of the log is equal to the base of the exponent you're taking the log of, so we haven't learned about ln yet, it'll come up on another slide, but ln of x is the same thing as the log of x base e. So when you see ln, it's called a natural log, and the base is e. So whenever the base of the log and the base of the exponent are the same, it's going to equal the exponent, because if you were to put this in exponential form, our base would be e, base answer, our answer would be e to the 4th, and our exponent would be x. What does x have to be in order to equal 4? Well, it's got to be 4, right? X is 4 because the bases are the same, so the exponents have to be the same. Last but not least, the log of 4 base 8. So, alright, let's put an x there as a placeholder. Now we'll do base, answer, exponent. So we have to reduce x 8 to get to 4. It can't get bigger, because if we square 8, we'll have a 64. If we take the square root of 8, it's going to be an ugly irrational number. So let's take the root. So we know that it's got to be a cube root, and then the cube root of 8 is 2. So you square 2 to get to 4. So the answer is 2/3. So when that happens, when it's not like a perfect, factor, take the root first and then raise that to a power to get back to 4. So the cube root of 8 is 2. Square that and you get 4. So there's a little log practice. So properties of logs, anytime you take the log of 1, it's going to be 0, because if you put this in exponential form, anything to the 0 power is 1. And anytime the base of the log, or you take the log of the base, it's going to equal 1, because anything to the first power is itself. And then anytime you take the log of something where the base of the exponent is the same as the base of the log, it's going to equal the exponent. Just put it in exponential form, it'll make sense. Base, answer, exponent, and you have both sides are equivalent. Alright, and if you ever have the log of one thing equals the log of another thing, and the bases are equal, then you could set what's inside the logs equal. Alright, now let's graph some loggies. Oh, last thing, forgot about this slide, should have put it earlier. If you ever just see log, like on your calculator, it might just say log. It's the log base 10. Alright, 10 is called the common log. So just like you don't put a 1 in front of x when you write x, if you just write log, it's assumed it's the log base 10. And you always got to take the log of something, so I should have put an x there and there. If you see ln, that stands for the natural log, so you got to put an e as your base. And if you ever need to change the base, use the change of base formula. So the log of b base a is equal to the log of b over the log of a. So some calculators only let you do like the log base 10. So if I wanted to figure out, what power do you raise 2 to get 7, and I can only use the log base 10, that's going to equal the log of 7 over the log of 2. And remember, when you don't write the base, when you just write log, it's assumed it's base 10. Alright, this would also equal the natural log of 7 over the natural log of 2. Alright, and when we go into properties of logs, we could prove this change of base formula just using what we know about exponents. But we're not going to do it yet because we don't have the tools yet. Oops, what happened here? Exit full screen. Alright, so graphs of logs. So logs are just the inverses of exponential functions. So if you, back to the previous video when we graphed y equals 2 to the x power, we knew this was 1/4, this was 1/2, this was 1, 2, and 4. Alright, so if you plugged in x there, then if you wanted to find what the graph of y equals the log of x base 2, you would take its inverse and just switch all the x and y's. So it would look like this. So those are what the points would look like, and then graphically they'd look like inverses. They'd be reflections over the line y equals x. Alright, so that's a quick sketch of this is what 2 to the x would look like. And this is what y equals the log of x base 2 would look like. So let's so you can see a little better, let's plot this out. So in green, I'll do y equals 2 to the x power. So remember, when you plug in 0, you got 1. And when you plug in 1, you got 2. And when you plug in 2, you got 4. And when you plug in -1, you got 1/2. And when you plug in -2, you got -1/4. So the graph would look like this. And the asymptote would look like that. So now y equals the log of x base 2. Now we're going to take all these points and switch x and y. So instead of having 0, 1, we're going to have 1, 0. And instead of having 1, 2, we're going to have 2, 1. And instead of having 2, 4, we're going to have the point 4, 2. And instead of having -1, 1/2, we're going to have 1/2, -1. And instead of having an asymptote at y equals 0, there's going to be an asymptote at x equals 0. So if you connect these dots, you see it, right? That's what the graph of the log of x base 2 would look like. It's a reflection over this line, y equals x, because we got the graph by just taking x and y and switching them. And that's the rule for reflecting over y equals x, and the rule for every inverse. So, how to graph it? 2 ways. One, if you look at the bottom, you can use transformations. So if you know what a basic log looks like, you could use transformations and find a special point and graph it that way. Or you could isolate the log expression, convert it in exponential form, and plug points in. So let me explain what I mean. So we'll come back to this. Well, first, a couple more things about log graph. So the domain is going to be, since you can only take the log of positive numbers, the domain is you take what's inside the log and set it greater than 0 and solve. The range is going to be all real numbers because the domain of exponentials are all real numbers and the log is an inverse, so you switch the domain and range. Special point is going to occur at when you take the log of 1. So you can't take the log of 0 because you can't raise a number to a power and get 0. But anything to the 0 power is 1. So if you figure out what makes, bx minus h equal to 1 and you solve, that's going to make this entire log expression equal 0, and then you could just solve, you could plug that in and solve for y, and you get your special point. Logs are going to be increasing graphs. They're going to have vertical asymptotes at the value that makes what's inside the log 0. And if a is negative, it's going to reflect over this line, this vertical line, the asymptote. So let's graph. So let's do it both ways. First, let's do it the exponential way. Let's isolate the log. So you have y minus 3 equals the log of 2 minus x base 4. And now we could put it in exponential form. So to put it in exponential form, so your base is 4, base answer, your answer is 2 minus x, and your exponent is y minus 3. Alright, and then you could isolate x and bring the x over on this side, and then 2 minus 4 to the y minus 3 power. Alright, now we could make a table of values, except we're going to choose numbers for y. Y is going to be our independent variable, and then see what x is. So when we plug in 3 for y right here, we get 2 minus 4 to the 0 power. So 2 minus 1, and you get 1. So there's 1 point. And then if you plug in 4 for y, you would get 2 minus 4. So it'd be a -1. And let's see, if you plugged in, you could just keep plugging in points. If you plugged in 5, alright, you would be 2 minus 4 squared, 2 minus 16, -14. And if you plugged in 2, it would be 2 minus the square root of 4, because it'd be 2 minus, wait, it wouldn't be. It would be 2 minus 4 to the negative 1 power. So it would be 2 minus 1/4. So it would be 1.75. Alright, so right now, that's how you could find, 5 points on your graph. Ah, crap, I wrote this weird. It should be 1.75, comma 2. So you got 4 points on your graph. Alright, and we can start by plotting some of those points. So you got, let's see, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So we got 1, comma 3. We got negative 2, comma 4. Sorry. And then negative 14, comma 5. So there's going to be like a point over here somewhere. And we're going to have 1.75, comma 2. So it's like right there. Alright, so we see this general form of the graph, and we know there's an asymptote, so let's find that. The asymptote is always going to occur at the value that makes what's inside the log 0, because you can't take the log of 0. The domain is going to be all the x values that makes what's inside the log greater than 0. So if we just solve for x in this expression, we get x is less than 2, which means we're going to have an asymptote at x equals 2. Alright, so here's our asymptote, and here's what our graph's going to look like. Oops. We got 3 points on it. 1, 2, 3. Screw that point. It's not really drawn to scale, so it came off weird. That point should be over here anyway. We got our asymptote, and there you go. So that's what this graph would look like. So again, to recap what I did, I found a bunch of points by isolating the log expression right here, and then putting it in exponential form, and then choosing numbers for y, and then solving for x. And I got, 4 good points. And then I found the domain by taking what's inside the log and saying it has to be greater than 0, and you got x was less than 2, and then that gave me my asymptote at x equals 2, and then I just connected the dots going right to the asymptote without touching it, and there you go. I got my domain was right here. My range is all real numbers. And I apologize for picking such ugly colors. It just kind of happened. Alright, domain of logs. So, let me pick a nicer color. Let's go with pink. No, purple? No. Can't decide. Yeah, let's go with purple. Color of royalty. So, to find the domain, we're going to take what's inside the log and say, alright, that has to be greater than 0. Boom, that's done. What's inside the log, and that has to be greater than 0. So you get x is less than 2. Boom. Here, we take what's inside the log, and it has to be greater than 0. So for this, we would have to factor and find our critical numbers. And when we tested 0, it would not have worked. But when we tested like -3 and 3, it would work. So the domain here would be all real numbers from -infinity to 2, and then from 2 to infinity, not including 2 or -2. That should be a negative right there. Alright, I believe that's it. Yep. Alright, I'm going to go get a haircut, but thanks for watching, and I'll see you in class.